Bismillahirrahmanirrahim. Assalamu alaikum dear students. Hope you are all fine and revising the lectures well. I am Fbise from Department of Physics. Today I am going to deliver lecture 20, chapter 12, current electricity. Previously in lecture 19, we discussed and we derived unit of electric power. We analyzed some numerical problems and we calculated maximum power output theorem. After listening to today's lecture, you would be able to understand thermocouples, variation in thermoelectric EMF with temperature, resistance thermometers, and Kirchoff's law KCL. First of all, we come to thermocouples. As it is indicated from the word thermocouple, therm means temperature, couples means two, pair. In early 1821, Thomas C. Back searched experimentally for a relation between electricity and heat. He joined two wires of dissimilar metals to form a circuit. You can see in the given figure, there are two different metals. These are a combination of bimetallic wires. One is iron, other is copper. These are joined to form a circuit. This is a circuit A to B. He discovered that if one junction is heated to a high temperature and the other junction remains at a cooler temperature, then the galvanometer connected at other end shows a deflection. Junction means meeting of two wires, the point where the two wires meet. So there are two junctions. One is maintained at higher temperature, other is maintained at a cold temperature, that is at a lower temperature, and when we join these two junctions with the terminals of a galvanometer, then what we observe? We observe a deflection in the galvanometer. What does it mean when a galvanometer deflects? That shows the presence of electric current. This effect is known as Seebeck effect. The EMF generated in the circuit is called thermoelectric EMF. The resulting current is known as thermoelectric current. The two-junction circuit is called a thermocouple. So this device is known as a thermocouple, where there are two junctions. You can see here two dissimilar metals. One is metal 1, other is metal 2. One is red wire, other is blue wire. When these two are joined, making a junction, and this junction is linked, it is connected with some hot reservoir, that is a candle, and here it is connected with the terminals of the ammeter, that is measuring the current in that is this is the galvanometer and measuring the voltage in millivolts. The two junction circuit is called a thermocouple. In this process, heat energy is directly converted into electrical energy. The wire pairs can be composed of noble metals such as platinum, iridium, silver, osmium, gold, and rhodium, or base metals such as copper, iron, nickel, copper alloy, lead, and zinc. Thus, it remains true for any pair of metals. Thermocouples are the most widely used temperature sensors in industry due to their less cost, simplicity, size, and usable temperature range. The electromotive force, that is epsilon EMF, is a function of the temperature gradient. When temperature changes, there is an EMF which is produced. The thermo EMF produced is very small, of the order of millivolts per every degree of temperature difference, that is delta T. The Seebeck effect is reversible. It means it could be retraced. It could be started in reverse order. That is, if the hot and cold junctions are interchanged, the direction of EMF and hence current, it may reverse. The greater the separation of the metals forming the thermocouple in the series, greater is the thermo EMF produced. The thermo EMF of many thermocouples has been measured as a function of the temperature T of the hot junction when the cold junction is maintained at 0 degree Celsius. So the two junctions are maintained at two different temperatures. One is hot, other is cold. Cold is maintained at 0 degree Celsius. Its temperature dependence is given by, so the EMF which is produced is given by epsilon, and here is a relation which is coming up to understand the working of thermocouple, and that mathematical relation is given by epsilon is equal to alpha T plus half beta T square, where in this equation alpha and beta are the constants, and these constants are called thermoelectric coefficient, and these the values of alpha and beta, it depends upon the nature of the metal, which metal you have selected to make the two junctions. All right. let we come to laws of thermocouple. For this purpose, let we take two strips, metallic strips, two different metals forming two junctions. We have joined here at this point the junction, at this point the other junction. At this junction it is linked with a high temperature, that is a flame, and here is a cold, that is cold water, and the two terminals are connected with the terminals of the ammeter, and the ammeter is giving you some current, right? So in this way we notice that the heat which is produced is converted into electrical energy. Now what we do here, we increase the intensity of the flame. By increasing the intensity of the flame, what we notice that the current which is produced, it increases. So this effect, as I told you, is known as Seebeck effect. Alright, in case of Seebeck effect, we convert heat energy into electrical energy. Now we deal with laws of thermocouple. The first law is law of homogeneous circuit, law of intermediate metals, and law of intermediate temperatures. Now we come to the first law, that is law of intermediate. A circuit composed of a single homogeneous metal cannot generate an electric potential by the application of even sufficient temperature difference between two different points of the circuit. So you can see here T1 and T2. Even we have two junctions but not similar. These are similar metals, not dissimilar, so producing no electric current. Law of intermediate metals. In case of law of intermediate metal, what we say, the net EMF in a circuit consisting of an interconnection of a number of unlike metals maintained at the same temperature is 0. So if we deal with number of unlike metals and they are operating at the same temperature, then the net EMF is equal to 0. So you can see here the two strips, that is T1 and T2, and here these are connected with the terminals of the ammeter, and what it results, it is shown over here. Okay, now variation in thermoelectric EMF with temperature. The figure shows an arrangement to study the effect of temperature difference between the two junctions in a copper iron thermocouple. So you can see here we are having two bodies. One is hot and other is cold, and we are taking two different metals, that is copper, iron. So this is giving you copper wire connected with the hot oil, and this is your second metal, it is iron, it is connected with the cold metal. keeping the junction in B at 0 degrees Celsius. So 0 degrees Celsius means at ice. Keeping the junction B at 0, the temperature of the junction A is increased. When both the junctions are at the same temperature, there is no thermo EMF. So what is important? Temperature difference is important. When there is no difference in the temperature, if both the junctions are maintained at the same temperature, means delta T is equal to 0, then there would be no epsilon. The thermo EMF increases with temperature and reaches a maximum value at a certain temperature called the neutral temperature. So when there is a change in the temperature, so the value of thermo EMF, it increases to its maximum value, and that temperature is known as neutral temperature, indicated by the symbol Tn. The value of the neutral temperature is constant for a thermocouple, depends on the nature of the materials. Which type of metals you have used, it depends, and is independent of the temperature of the cold junction. As the temperature of the hot junction is increased, the thermo EMF starts decreasing. So you can see here that here is the neutral temperature where the EMF is maximum. But what happens when we further increase, then when we increase the temperature of the hot junction, the thermo EMF starts decreasing instead of increasing, which is shown by theta I. That is inversion temperature. The particular temperature at which the thermo EMF becomes 0 is called the inversion temperature. So this is the neutral temperature, and this is giving you the inversion temperature. The graph shows the variation of the thermo EMF with the temperature of hot junction with the cold junction. Resistance thermometer. Resistance thermometers are called resistance temperature detectors, that is RTDs. Are sensors used to measure temperature by correlating the resistance of the RTD element with temperature. So in this case, in case of resistance thermometer, we measure the temperature by changing the resistance of the sensor. That's why these are known as RTDs. Common RTD sensing elements constructed of platinum, copper, or nickel have a unique and repeatable and predictable resistance versus temperature relationship. So this relationship which exists in between R and T, we construct this resistance thermometer, and operating temperature range, different temperatures is observed. The R versus T relationship is defined as the amount of resistance change of the sensor per degree of temperature change. The relative change in resistance, that is temperature coefficient of resistance, varies only slightly over the useful range of the sensor. Platinum is the best metal for RTDs. That's why we use it, because it follows a very linear resistance temperature relationship, and it follows the R versus T relationship in a very repeatable manner over a wide range of temperature. The unique properties of platinum make it the material of choice for temperature standards over the range of minus 185 degrees Celsius to 630 degrees Celsius. They are slowly replacing the use of thermocouples in many applications below 600 degrees Celsius due to higher accuracy and repeatability. Okay, we come to the working of resistance thermometer. In industrial measurement technology, various types of electrical thermometers are used. One of the most commonly used is the resistance thermometer. It measures temperature using electrical resistance. The heart of the resistance thermometer is the platinum measure resistor, which measures values defined by standards. If the temperature changes, the electrical resistance in the sensor either increases or decreases following a precisely defined characteristic curve. By measuring the resistance, the temperature can be determined very accurately. Before moving further, before moving towards circuit diagram, here is an information for you. Lactic schematic circuit symbols, because while dealing with the circuit diagrams we deal with different type of symbols. We must know how to read these symbols. What do you mean by these symbols? So in the first box here, if there are two bars, one is bigger one stands for positive, the smaller one stands for negative, so it means this is the function. It stands for a cell, and cell is a source of current electricity. Now in the second case here, so there are 1 2 3 bars, big bars, and 1 2 3 small bars, so this stands for a battery. Two or more cells joined together, this battery is made of 3 cells. This is the description of this symbol. So in the third symbol, when we deal with such type of symbols, then we must understand this stands for light bulb, which converts electrical energy into light and thermal energy. So when we deal with this symbol, that is a circle and capital M is written, this stands for electric motor, which converts electrical energy into mechanical energy. So while dealing with this symbol, you can see here two dots and this line, and when these two are connected, it means circuit is closed. So we can have such type of terminals, 1 2 3 terminals, two ways. So this stands for switch, that is knife, or it may be knife, or it may be a button. It can be open to stop a current or closed to allow current to flow. So when we deal with this type of symbol, stands for a fuse wire. This prevents too much current from flowing through a circuit. It will break during a circuit and protect the circuit. So inside the circle, if capital A is written, it stands for ammeter, which measures current in amperes, and it may be in milliamperes, and vice versa in microamperes. It stands for flow of electrons. So a circle, and inside it capital V, it stands for voltmeter, which measures voltage in volts, that is potential energy. So while dealing with this symbol, you people are familiar with it. This stands for resistor, which is a device which impedes or slow downs the flow of electrons. And while dealing with this symbol, so you can see it stands for ground connection. So we deal with potential difference, and potential difference means two levels. One must be higher level, other must be lower level, and at the lower level, so we can ground it, that is making 0 volt level. So it connects the circuit to the earth, that is known as grounded. Kirchoff's law. Sometimes we encounter circuits where simplification by series and parallel combination is impossible. Consequently, Ohm's law cannot be applied to solve such circuits. This happens when there is more than one EMF in the circuit, or when the resistors are connected in a complicated manner. So, dear students, we noticed previously where we deal with the components of circuit like capacitor or a resistor or any other electronic device with the one source of energy, then such type of circuit could be solved by using simple Ohm's law. But what happens when we have some different components, like we have two sources of EMF which are connected in a circuit, or the series and parallel combination of resistors are connected in a very different way. So such type of circuits are known as complex circuits, and we are unable to solve the problems of complex circuits by using simple Ohm's law. In case of Kirchoff's law, you can see here in the given figure how many sources, how many batteries. There are two batteries, epsilon 1 and epsilon 2, and how many resistors which are connected. There are three resistors, that is R1, R2 and R3. In figure 1, it shows circuit containing two sources of EMF and three resistors. This circuit cannot be solved by series and parallel combination. We are unable to apply the rules for series combination of resistors or parallel combination of resistors, or we are unable to apply a simple Ohm's law, that is V is equal to I R directly to solve the problem. So while dealing with such circuits, we need another law, and in this case you can see in figure 2 that even there is a single source epsilon, but how R1, R2, R3, R4 and R5, how they are connected? They are not connected in series, they are not connected in parallel, so they are making such type of loop. So simple Ohm's law or simple rules for parallel and series combination of resistors are unable to solve the problems of such complex network. So this figure is unable to be solved by using simple laws. Through this circuit has one source of EMF. It cannot be solved by using series and parallel combination. Resistors R1 and R2 neither in series nor in parallel as it is shown in the given figure. In order to solve such complex circuits, there was a German physicist named Gustav, this is TAV, Gustav Robert Kirchoff, 1824 to 1887. He gave two laws known as Kirchoff's laws. Two laws, and here two laws. The first law, Kirchoff's first law, this first law is known as Kirchoff's current law and abbreviation is KCL, and Kirchoff's second law, KVL, we will discuss it later. Now here first of all we come to Kirchoff's current law and it is known as KCL law. This law is related to the currents at the junctions of an electric circuit. Any may be stated as under. So the statement of KCL, the algebraic sum of all the currents meeting at a junction and in an electrical circuit is equal to 0. That is, sigma I is equal to 0. As we all know, sigma stands for sign of summation. Sigma I means that you are summing up all the currents which are flowing at a junction and its algebraic sum is equal to 0. You can see here in this figure, this point O is giving you the point of meeting of different wires or conductors. A junction is point in a circuit where two or more components are connected. So this is a junction which is a point in a circuit where more than two components are connected. So you can see at O different components are connected. As algebraic sum is one in which the sign of the quality is taken into account. So sigma I is equal to 0. What does it mean? You can see here, consider four conductors here, and through four conductors, four currents are passing, I1, I2, I3 and I4. So this is conductor 1, through it I1 is passing. This is conductor 2, I2 is passing. This is conductor 3, I3 is passing. And this is conductor 4 through which I4 is passing. But we notice one thing, the direction of flow of current. I1 is moving towards the junction O, alright. I4 is moving towards O, alright. While I2 is moving away from the junction O. I3 is moving again away from the junction O. If we take the signs of currents, now we come to the sign convention for the flow of currents. The sign convention for the flow of current which is moving towards O, it is taken as positive. And the currents which are flowing, which is moving away from the point O, that is the junction, it is assigned as a negative sign. So according to the statement of KCL law, that is sigma I is equal to 0. Let me sum up all the current. Algebraic sum of all the current which is passing through four conductors is it must be equal to 0. But do remember the sign convention. So it means I1 and I4 as they are moving towards O. So the sign convention would be positive. It means I1 plus I4. Alright. But the sign convention for I2 moving away from O, I3 moving away from O. So I2 and I3 are taking as negative. Now we apply the statement of KCL, sigma I is equal to 0. What does it mean? I1 plus I4 plus minus I2 plus minus I2 is equal to 0. It means I1 plus I4 minus I2 minus I3 is equal to 0. Alright, what we can take over here? We can take negative sign common, and inside the bracket what would be left? I2 plus I3. Alright, then we shift these two currents on the other side of the equation. So we get here I1 plus I4 is equal to I2 plus I3. What does it mean? Read it, students. It means the algebraic sum of all the current moving towards the junction is equal to algebraic sum of all the currents moving away from the junction. That is, sum of incoming current is equal to sum of outgoing current. Hence, Kirchoff's current law may also be stated as the algebraic sum of currents flowing towards the junction in an electrical circuit is equal to the algebraic sum of currents flowing away from that junction. Kirchoff's current law is true because electric current is merely the flow of free electrons, as we know. What does it mean when we deal with the current? Current is the flow of charge. Rate of flow of charge is known as current. So this Kirchoff's law is true because current means flow of electrons, and they cannot accumulate at any point in the circuit because electrons, they always move. Current means flow of electron. Where they move, they may be moving towards the junction. They may be moving away from the junction. This is in accordance with the law of conservation of charge. Hence, Kirchoff's current law is the base of law of conservation of charge. So, we can have here another example of KCL law, that is Kirchoff's law. And in case of this Kirchoff's law, that is again sigma I is equal to 0, and sigma I is equal to 0. For this purpose, let me take here the resistors, 4 resistors, that is 5 resistors, 1, 2, 3, 4 and 5. But we notice the direction of flow of currents through the resistors, that is moving towards the current, or they may be moving away from the current. They may be moving towards the junction or away from the junction. All right. Towards the junction. So I4 towards, I5 towards, I3 away and I2 away. So another example, you can write down I1 plus minus I2 plus minus I3 plus I4 plus I5 is equal to 0. So it could be written as I1 plus I4 plus I5 is equal to I2 plus I3. So this is giving you another way to define KCL rule. As far as the laws of mathematics refer to reality, they are not certain, and as far as they are certain, they do not refer to reality. Thank you, girls.